following program is brought to you by Caltech.
Okay, so Mike's going to be telling us about some of the experimental attempts to constrain, in particular, a little bit higher frequency, non-21 centimeter spectral distortions in the CMB. Mike started out life at UCSB as a grad student. Now he's at JPL as a
research scientist
in the cosmology group. He's been involved with Planck, with Arcade, which I think you'll probably be talking about, and probably all sorts of things I don't know anything about. And we're going to start perfectly at 11:47, so we will make it to lunch at 12:27 on the dot. All right.
I want to complain about the lack of significant digits in the timing up there.
I'm so sorry.
All right, can you guys hear me okay? So I'll talk a little bit about spectral distortions and the limits on them from a variety of platforms. This will be mostly an introduction, so I won't go too detailed in some of these. But I'll cover the constraints from current and recent experiments, give you a description of some of them, the ones of which I'm most familiar, and try to say a few words about what I think are the next steps. In all of this, I will try to have a heavy focus on two areas of the experiments that I'm going to talk about. And those areas are calibration and foreground. So I'll try to say a little bit about calibration and foregrounds for each of the experiments I'll talk about, because I think it will be an important factor in the experiments we design next. So starting out with sort of the landscape of current experiments. So instead of plotting the overall Blackbody curve, here I'm just showing the temperature at a given frequency, in thermodynamic temperature, from 0.1 to 1,000 gigahertz. Fire-ass, which Jens talked about earlier, covers this range here, and the size of the error bars is thinner than the width of that line. So in addition to this great space experiment, we also have constraints from a number of ground and balloon experiments listed here. And generally speaking, the error bars are quite a bit larger. So this is the landscape today. Now I'm going to change the y-axis and show you the limits on various spectral distortions we have today. These are mostly from fire-ass. A chemical potential, or mu distortion, is limited at about 9 × 10⁻⁵, and that's this blue curve here. Compton Y distortion is limited at about 1.5 × 10⁻⁵, also from fire-ass, and that's this green curve here. And there's also a limit on free emission, also about just over 10⁻⁵. So despite the fact that these, in particular, the chemical potential distortion has its largest change right here, the source of our constraint from that actually is still from fire-ass. It turns out that the error bars are so tight here that this is really the best constraint on mu distortions to date. It's also the best constraint on Compton Y distortions. So I'll say a few things about fire-ass. I think this is one of the most important spectral distortion experiments we have, and I think it points the way to what we might think about in the future. Fire-ass stands for the Far Infrared Absolute Spectrophotometer. It's a polarizing Michelson interferometer. It measures the difference between the sky and an internal blackbody. So what happens is we have two inputs. There's an internal reference blackbody with a horn, and there's a sky horn here. And those two signals are inputs to a Michelson interferometer. It has movable mirrors here and here, beam splitter, and then there's sets of detectors here and here. So this is a bit like a Fourier transform interferometer. So this measures the difference between the sky and this internal load, and then periodically throughout the measurement, an external blackbody calibrator pops into the sky horn and moves out again. Okay. So here's a couple of pictures from the Kobe team. This is what the guts of the instrument look like. That has some of the parts removed. The moving mirrors will be are mounted over here. This is the FIRAS external sky horn. This is the black body, external black body calibrator. It pivots here and tips in, covers the feed, and then moves out of the way again. And so, of course, the famous result of FIRAS, a beautiful black body curve. Because it's an interferometer, people like to plot frequency as wave numbers, inverse centimeters. I don't think in inverse centimeters, so I put the frequency up here to remind myself of what these things are. And megajanskis per steradian is the y-axis. The errors are about 1 part in 10 to the 4 on this curve. It's conventional to show the results this way, to show the nice black body, but I think it's important to remember that what the experiment is measuring is an interferogram, and in particular an interferogram of the difference between the sky and the reference load. You imagine an ideal situation where the experiment is very close to operating in null condition. You can imagine the sky horn is looking at the sky. It has the external calibrator in place in front of the horn, and it pops out, and you don't see any difference in the interferogram. Then you know that the sky is the same temperature as your external black body. So the key to this experiment is not huge dynamic range in the detectors, but it's rather constructing your calibrator such that it's black and it's close to the same temperature as the thing that you're trying to measure. So the experiment is close to a null experiment. And that helps with a variety of systematic constraints. Taking away the overall blackbody curve, this is a plot of residuals from FIRAS, again with inverse wave number, or with wave number inverse centimeters, and now kilojanskis per steradian here. So the way one gets a spectral distortion measurement out of this is by doing a fit. And you do a fit of the data, intensity versus wavelength, to a black body with unknown temperature. But you also have to include a number of other factors. So you include the prospect that the calibrator is a slightly different temperature, and you do a first order expansion about the nominal temperature, so delta T times the derivative of the black body function with respect to temperature. Also, you admit that your galaxy removal may not have been perfect, and so you include a nuisance factor times a residual galaxy spectrum. And then one fits the magnitude of the spectral distortion in the limit of small distortions on top of that. So this is the fit that was done with FIRAS, and these are the limits that were derived, which were mentioned earlier. So let's take a look at the plot. The black line is the residuals from the fit, so it looks like scatter about 0, which is good. In the dash dot 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 line, that's this guy here. That's the effect of a 100 microkelvin temperature shift in the calibrator. So just having that calibrator off a little bit would allow, would create this kind of distortion, and of course that's fit in this term here. The residual galaxy has this kind of shape, and shown here is the plot of a quarter of the magnitude at the galactic pole. So that's the spectral shape of this term here. And then two different spectral distortions are plotted here. The dashed line here is the maximum Y distortion consistent with the data, and the dotted line is the maximum mu value consistent with the data. So just as Jens mentioned earlier, that you can have a spectrum that has a template that you can imagine fitting your data against. The same thing is essentially done here, where there's different types of spectral distortions. and one fits the data to try to match those over a wide frequency range. For galaxy modeling, the procedure that FIRAS used was to try to remove the galaxy using the Derby data from another instrument on COBE, and then do a fit of the residual emission of an emissivity and temperature to a nu squared B of t model with both the nu and the temperature, or I'm sorry, both the emissivity and the temperature fit. And the temperature came out to about 9 Kelvin. So that could be, that could indicate that there's some cold dust in the galaxy that wasn't picked up by Derby, or it could just be an artifact of of what was left in the residuals. Synchrotron, free emission, extragalactic radio sources were not included in this list. And so if one wanted to repeat FIRAS and do better and dig deeper into the foregrounds, the first thing you might ask yourself is, how much better do I need to do against these simple models for foregrounds? The calibrator from FIRAS was really wonderful, actually. It's a great black body. This is a schematic diagram. It looks like sort of a cone with a V here, and that's so that any radiation being emitted from the instrument gets many bounces before it's reflected back. That helps make the black body as black as possible. The reflectivity was measured to be better than about 3 parts in 10 to the 5th. The gradients in the black body were less than a millikelvin, and I'll say a bit about that a bit later on in the talk. And precision thermometry, 0.2 millikelvin precision and 1 millikelvin accuracy. So you actually know what the temperature of this black body is very accurately. Okay, so going back to our landscape here. So this is what FIRAS did. And so now you ask yourself, how can we do better than this? Well, for a long time there's been a considerable emphasis on lower frequency measurements, ones that can be done from the ground. As I'll mention in a bit, the atmosphere is largely opaque at 60 gigahertz, and then there are narrow windows in which it's transparent at higher frequencies. But it's been natural to try to make progress at lower frequencies. And in the post-FIRAS era, it was perhaps even more compelling to try to limit mu and Y-free distortions by looking at about 10 gigahertz. And from this plot, you can see if you could do 1 millikelvin error bars, or maybe 2 millikelvin error bars, at around 10 gigahertz, or maybe a little bit lower frequency, one could make progress against these constraints. So one of the things that you can immediately recognize is that if you're operating the ground, even at a very dry site like the South Pole, you have to look through the bulk of the atmosphere, and that's an issue because if you take a look at the atmospheric emission spectra from a variety of great sites like the summit of White Mountain, or near the summit of White Mountain, and at the South Pole, the atmospheric emission at 10 gigahertz is about a Kelvin. The dotted line here is a dry atmosphere model, and the two solid lines include water vapor with a variety of contributions. But about a 1 Kelvin contribution at 10 gigahertz. So if you want to dig down to 1 millikelvin error bars, it's hard to measure, model, and remove a 1 Kelvin signal from that. So that's motivated a number of groups, including one that I'm involved with, to go to balloon altitudes, where the emission is much lower. This is a picture of an experiment called Arcade 1, the absolute radiometer for cosmology and diffuse emission, with these cast of characters from Goddard, UC Santa Barbara, and JPL. This is in Fort Sumner, New Mexico. You can see the balloon here. This is the launch vehicle. And this is the experiment here. This is a liquid helium cryostat with a lid. the instrument electronics, batteries, and other gondola electronics over here. So the concept of this experiment is to have a liquid helium dewar in which the instrument resides, and to have a lid that's closed while the experiment is being launched. And once it reaches an altitude of 100,000 or 110,000 feet, the lid opens up and you look out. One of the things that we wanted to do with this experiment was to not have a window, not have a piece of plastic or glass between the instrument and the signal. And the point of that was, well, one, there's residual emission that can come from any such window. And two, it's a great site for contaminants to land on and contribute even further to your signal. So how do you get an instrument cooled to approximately the same temperature as the background you're looking at, in this case 2.7 Kelvin? How do you get that to survive with no window? Well, the idea here was to have helium gas that boils out of the dewar, forms a cold puddle of gas, and that serves as a thermal barrier between the instrument and the residual atmosphere outside. I'll show you how that worked in a bit. Another feature I want to emphasize from this diagram is that we've tried to put the dewar off to one side of this rotator, assembly, and flight train. This is to get some of this mechanical hardware out of the near side lobes, or even maybe the far side lobes of the antenna beams, to limit its contribution. So this is what I was trying to describe earlier with a cold puddle of helium gas here. This is a schematic diagram of the instrument. There's a superfluid helium bath at the bottom. Superfluid fountain effect pumps pump liquid helium up to the top to cool these flares on the side. And also there's a superfluid helium pump that pumps liquid helium into this external calibrator facility. The calibrator moves back and forth and covers different antennas in turn. So one antenna would look at the sky while another is being calibrated. And the idea is to regulate the instrument at 2.725 Kelvin. So try to get the experiment in thermal equilibrium with the radiation that we're trying to look at. If the instrument is at 2.725, the blackbody is at 2.725, and the radiation is at 2.725, then small reflections or additional sources of emission can be small and not have a large effect or have a large systematic impact on the data. The Arcade 1 version of this was instrumented with 10 gigahertz and 30 gigahertz receivers. So this is a picture of the top of the cryostat. What you see here are these cold flares that surround the ring. This is the 30 gigahertz feed horn that's looking out at you. And this is the calibrator assembly. Right now it's covering the 10 gigahertz horn. And during the flight, this thing moves back and forth in this direction. And I think you can see some of the wear marks here. It covers the 30 gigahertz horn, and then the 10 gigahertz gets to observe, and vice versa. You can also see a large number of pinholes. This is where cold helium gas flows out of these little pinholes and keeps the ambient atmosphere from freezing onto this 2.7 Kelvin surface. We have photos and video camera from flight, which unfortunately don't show up very well on a computer screen, but you can see from that there is a little bit of condensation from nitrogen on the edge here in flight, but it doesn't build up with nitrogen ice on the surface during flight because of that outflow of helium gas. This is the instrument during construction with some of my colleagues. This is for scale, this gives you an idea of the size of the dewar that we're talking about. These are the cold flares, and Al Kogut here is doing something with the calibrator. This is the lid that's closed for launch and opens up at altitude. And there's a magnetometer assembly for pointing location there. I think we're losing this. Okay. So our goal was to get 1 millikelvin error bars at 10 gigahertz. We didn't hit that. We hit about 10 millikelvin error bars. So this experiment wasn't an improvement in the spectral constraints over FIRAS. It was the tightest measurement at 10 gigahertz, but not tight enough to improve the limits on mu distortions. But we felt it was a good validation of the technique and motivated us to try to build a more ambitious experiment. And on a personal note, one of the fun things about ballooning is that you get to have items that say NASA critical spaceflight item, handle with extreme care, to be all scratched up and muddy when your payload lands on the ground. The calibrator for this experiment, this is a cross-sectional view. It's a series of teeth here to, again, provide multiple bounces to make this black. The absorber was made out of an iron-loaded epoxy again. We also had pretty good thermometry with precision of about 0.15 millikelvin and accuracy of 2 millikelvin. Unfortunately, one of the things that limited our experiment was that there were gradients in the calibrator from the front edge to the back of about 0.7 Kelvin. That's driven largely because that focal plane was colder than 2.7 Kelvin, and so we had cold teeth and a relatively warm back, and that's in part because the focal plane it turned out to be difficult to regulate at 2.7 Kelvin, but it was easy to make it colder, so we did. The foregrounds for 10 and 30 gigahertz were derived from a combination of WMAP and the Haslam 408 megahertz map. And in magnitude, they're about 1.4 millikelvin and less at 10 gigahertz and less than half a millikelvin at 30 gigahertz. And the uncertainty in this is driven largely by the uncertainty in the spectral index between the WMAP and 10 gigahertz and the 408 megahertz map. So as I said, we were motivated to try a more ambitious version, which we called shockingly enough Arcade 2, with a couple of additional colleagues. This is a picture of the instrument on the launch vehicle in Palestine, Texas. This is the cryostat. A couple of things to point out now. This is a larger diameter mirror, larger diameter dewar. It's now big enough that we can't cantilever it off to the side like we did with Arcade 1. And so there is flight hardware that's immediately above the dewar. And we dealt with that in two ways. One, that the horns look off to the side. And two, we have some pieces of flat honeycomb aluminum on each side. And the idea is that any radiation that might come from above is intercepted by this panel. And if you think about this in reverse, like I do, photons coming out of the feed horn hit this panel and are reflected to the sky and not to the ground, and they don't bounce off of some rigging thing and get reflected to the 300 Kelvin ground. This is a picture of some of the integration. This is the calibrator now. So this is this whole assembly gets mounted on top of the various receiver horns here. It rotates, so this calibrator covers some of these feed horns while others get to look through this hole to the sky. And then it rotates, and this calibrator covers other feed horns. This thing is about this big around. We like to call this the flying cold tub. This is the size of the instrument section. This whole thing gets inserted into this cryostat. It's about 1.5 meters open aperture. It's launched with 1,800 liters of liquid helium. That's a lot of fun. Oh yeah, so one of the fun things about this is, so you have a whole bunch of liquid helium here. It's boiling off on the ground because it's Texas in the summertime and it's 90 degrees outside and 90% humidity. So you get a lot of boiling helium, and that boiling helium turns into cold helium gas, which has to go somewhere. And the real trick is to have it go somewhere without freezing everything, without turning this top section into a solid block of ice, which would then prevent the lid from opening. And through process of experimentation, we discovered that one of the best ways to do that was to have some of the gas go up through this lid here, which has a number of radiation shields, and so it cools those shields as it winds up. And then it goes out the top. And you can see this little yellow and black snake here. That's a little piece of dryer ducting that carries some of that gas away. We don't let it just go out the top because the gas would go out of the top very quickly, and it would tend to suck a little bit of water vapor in around the edges. So if you put this level right at about that same level, then you get gas flow out the top, and you get a little bit through the sides, and then everything is just about right, and you don't get a big solid block of ice. The results from our first flight, we didn't get to 2 millikelvin at any of these frequencies either. Our second flight, we got closer. We got to about 5 millikelvin near 10 gigahertz. So still not quite enough to limit mu distortions compared to FIRAS. One of the other things I wanted to emphasize was systematic control. This is a table of systematic contributions to the error budget. These numbers are all in millikelvin. And on the top are 3 gigahertz, the low and high frequency subchannels of 3 gigahertz, 8 gigahertz, 10 gigahertz, 30 gigahertz, and 90 gigahertz. And then various contributions and then the totals. At low frequencies, we're driven by side lobe illumination of some of that spreader bar, some of the mechanical rigging in the experiment. At high frequencies, we're driven by residual emission from the balloon. And in all, around 10 gigahertz, our error is just under 3 millikelvin. This is something that you can imagine modeling and removing to maybe 1 part in 10 or something like that. But I think through this experiment, we convinced ourselves that doing better than 1 millikelvin from a balloon experiment is going to be very difficult, because anything that you can think of to help some of these systematic error limits will help some of these columns, but not all of them. Some of it will make them worse. And some of these are modeled, and some of them are measured by attempting to change the temperature of the item in flight and using that as a bound. The balloon is a modeled number from the side lobes, assuming something about polyethylene. And I think the same is true for the suspension numbers. This is a close-up of the calibrator. Again, this is stainless steel loaded epoxy. A whole bunch of little cones, 26 ruthenium oxide resistance thermometers embedded in these guys. With a NIST, the thermometers are calibrated against NIST, a NIST thermometer, to an absolute accuracy of about 1 millikelvin. We were able to take these thermometers and cross-calibrate against the NIST thermometer multiple times, separated by several years, and retain this 1 millikelvin accuracy. So I think we're convinced this is a good number for the absolute accuracy. And the precision of the readout is again about 0.15 millikelvin. And again, we had some difficulties with front to back gradients between the tip of the cone and the back of the cone in flight of about 600 millikelvin. And we had about 20 millikelvin transverse gradients in flight. Generally, just operating this guy in the residual atmosphere has been leading to the gradients, and I think has convinced us to some extent that that balloon altitudes offer a hope to do well, but it's hard to do a lot better than what we think we've already done. Of course, one can also get above the atmosphere entirely by going to a sounding rocket, as shown in this work from Gush, Halpern, and Wishnow. Shortly after Kobe's result. You get freedom from the atmosphere, but it's generally a short flight, and there's always concern about residual rocket exhaust or other things that you drag up with you, so that's been a problem for some other experiments. This particular rocket experiment was also a polarizing interferometer. In this case, it looks very much like FIRAS. There's a black body on one horn and just sky in the other. This particular experiment did not have an external in-flight calibrator, but was rather just calibrated on the ground with an external calibrator covering this horn. It was removed and then launched. So I'll wrap up with a few words here. So I think in going to the next step, raw sensitivity is not a fundamental limit. Certainly the balloon experiments that we've flown so far have not been limited by the raw statistical precision of the detectors. And there's quite a long ways to go before it becomes even a minor concern. Of course, well, with Arcade, we just had one receiver at each frequency, but if sensitivity ever did become an issue, you could imagine having many horns, maybe 100 horns, to improve the sensitivity. A number of ground-based anisotropy experiments are hoping to push sensitivity to the tens or 100 nanokelvin level. So if they can get that sensitivity, so could a spectrum experiment. Important ingredients for improving on this are foregrounds and calibration. Instrumental systematics, I think, are also important, but I think we believe that we can model, identify, and control those to the point where these are not yet the limiting factor. It's really the foregrounds and calibration that are limiting us currently, I think. This week in our workshop, we're going to discuss a number of ways forward, including ground-based experiments and possibly also space-based experiments. Just as a sampling of space-based experiments that have appeared in the literature, something called PHI-RAS-2 appeared in the paper by Fixon and Mather, in which they suggested just rebuild PHI-RAS but with modern bolometers and attain higher sensitivity and spend more time of the mission dedicated to anisotropy or to spectrum measurements, specifically spectral distortions. The Diffuse Microwave Emission Survey, DIMES, was a mission concept studied at Goddard. This is sort of a super arcade, basically very similar to our arcade, covering 3 to 90 gigahertz. A proposal from the Italian group, which was very similar. And then more recently, something called PIXI, the Primordial Inflation Explorer. This is similar in concept to PHI-RAS or PHI-RAS-2, but instead of one horn with an internal blackbody calibrator, now both horns are on the sky all the time, and the calibrator alternately covers one feed horn and then the other, and then maybe neither. And that gives you greater control on systematics, because you can tell, because of the symmetry of the instrument, the systematics are very well rejected, and any asymmetries can be measured very effectively. So I'll stop there.
This program is brought to you by Caltech. Visit us at caltech.edu.